Hello friends, in the previous video, we have seen what is in by stress, what is in by strain. See, sometimes stress may be tensile, sometimes stress may be compressive. See, here, one more important topic, that is Hooke's law. When a material is loaded within its proportional limit, the stress produced is directly proportional to the strain. See, Hooke's law states that when a material is loaded within its proportional limit, the stress produced is directly proportional to the strain. See, here you can see that on the x-axis, strain is given, on the y-axis, stress is given. And see, this is the proportional limit. As stress increases, strain is also increases. The line is your straight inclined line. See, so stress is directly proportional to the strain. So sigma is proportional to the strain. So instead of this proportionality sign, here we are putting sigma is equal to constant into E, because we replace this proportionality sign by using this constant. So sigma is equal to constant into strain. So we know that sigma upon E, that is stress upon strain, is equal to constant. That is our Hooke's law. When a material is loaded within its proportional limit, the stress produced is directly proportional to the strain. See, so many syllabus topics are there. Here I am taking one by one, but you have to highlight each and every formula. You have to refer E content always. You have to highlight all the formulas that I am explaining here. Stress upon strain is equal to constant. So the another syllabus topic, that is modulus of elasticity. See, the ratio of stress to the corresponding strain is a constant. This ratio is known as modulus of elasticity, or you can say the Young's modulus. So that constant is nothing but capital E. So capital E is equal to stress upon strain. It is denoted by capital E. So the SI unit is Newton per mm square. That is very important. The unit of stress, that is Newton per mm square, and E, that is strain. Strain is unitless quantity. That is change in length upon original length, or you can say the change in dimension upon original dimension is equal to strain. So here you can see modulus of elasticity, or you can say the Young's modulus, is equal to sigma upon E. You have to highlight this formula also. See, another syllabus topic, that is elastic limit. You can see the stress strain diagram for ductile material. See, in the every question paper, generally they are asking stress strain diagram for ductile, or you can say the for brittle materials. You can see here, the Mumbai University, we have the question in May 2015, in the December 2015. The question is, draw stress strain curve for ductile material and explain its silent points on it. See, you can see this diagram. Here I am explaining the entire diagram. Just you have to refer this diagram. That is very, very important thing. Again, I am telling you, here just I am explaining each and every important syllabus topic. Just you have to highlight each and every point in E content. It will be more useful while solving the problem. See, here you can see in the x-axis, small e is given, that is strain. You have to concentrate on cursor location, that is very important. Here you can see on the y-axis, stress is given, from 0 to A to B, B to C, C to D, the curve is likewise. Again from D, it is increasing till point E. E to F, that is, you can see here, that is engineering curve. And here you can see the dotted curve, that is true curve, F dash is given. In this diagram, from zero, from you can see the origin point to this, that is elastic region. I will explain which is the elastic region. This one is the perfectly plastic region. You can see in this diagram, that is perfectly plastic region. This one is a strain hardening region. From this point to this, that is strain hardening. And here from this point to this, that is necking. So this diagram is very important. I will explain you each and every region to you. When a ductile material like mild steel bar of a uniform cross-sectional area is subjected to a gradually increasing tensile load up to fracture using universal testing machine, the relationship between stress and strain is generally of form as shown in figure. See, in the strength of material, universal testing machine is very important during the practical. You can see this diagram. You will get this type of curve for ductile material like mild steel bar. So once again, you have to see origin point to A to B, B to C, C to D, from D to E, E to F, and here E to F dash. See silent points of the curve. Already you know that limit of proportionality, that is point A. B is the elastic limit. This one is your point B, that is elastic limit. The point C, you can see that is upper yield point, that is point C. Lower yield point, that is D. Ultimate, or you can say the maximum load point, that is E. And breaking point, that is F. You can see here A, B, C, D, E, F. All points are given. See here, first point, that is A. It is limit of proportionality. In the range of OA, the strain or elongation is proportional to stress and the graph is a straight line. Point A is called limit of proportionality. It is the value of stress up to which the stress and strain has a constant ratio and Hooke's law is obeyed. That is limit of proportionality. So in the elastic limit, at point A, the curve deviates from the straight line and the stress strain graph from A to B is non-linear. So you can see in this diagram, from origin to A, that is linear, you can see the straight line, but from A to B, a small curve is there, so that is non-linear. So in the graph, from A to B is non-linear. If the load is increased beyond A up to the point B, the material behaves in an elastic manner, or you should aware with the elastic manner, that is, on the removal of load, the whole deformation will vanish. The value of stress corresponding to point B up to which the material behaves in the elastic manner is called as elastic limit. Up to point B, the material will be in the elastic range, and beyond B, it will be in the plastic range. The 2 points, proportional limit and elastic limits, are very close to each other, and in some cases they may coincide also. See upper yield point, In the diagram, you can see this is your point C, that is upper yield point. This is your point D, that is lower yield point. You can see upper yield point, that is point C is called upper yield point. At the point, there is an increase in strain, even though there is no increase in stress. That is your point C, that is upper yield point. The formation of creep makes the specimen plastic and the material begins to flow. The value of stress corresponding to point C is called as yield stress or yield strength. The yield stress defined as that unit stress which will cause an increase in length without an increase in load. At this stage, strain is about 0.125 and stress is about 250 Newton per mm square. That is point C, upper yield point. After the upper yield point, the next point, that is D, that is lower yield point. Load may rise and fall while yielding occurs. This is indicated by wavy appearance. You can see this wavy appearance in the diagram. See, this is the wavy appearance. You can see at point D is the wavy appearance. Of stress strain graph between C and D. Point D corresponding to the lower yield point after yielding has ceased at D. Further stress and strain can be obtained by increasing the load. The next point, that is ultimate load point, that is your E point. Already I have shown you in the diagram. After increasing the load beyond the yield point, the stress strain curve rises till the point E is reached, which is called as ultimate, or you can say the maximum load point. The stress is corresponding to this point is also maximum and is called ultimate stress or ultimate tensile strength or tenacity. This stress is about 370 to 400 Newton per mm square. At this stage, cross-sectional area at a particular section starts reducing fast. This is called as neck formation. And after that, there is a breaking load point up to point E. Cross-sectional area of specimen goes uniformly decreasing, forming a neck or crest, and the load required to cause further extension is also reduced. You can see this is the necking in the diagram, and this is the cup and cone failure. This is the cup and this one is a cone. It is cup and cone failure. As the elongation continues, the cross-sectional area becomes smaller and smaller. Ultimately, the specimen is broken at F into two pieces, giving cup cone type ductile fracture as shown in figure. You can see this figure here, cup and cone failure. Point F is called breaking load point and stress corresponding to point is called breaking stress, or you can say the rupture or breaking strength of material. At this stage, strain is 20 to 25%. So again, you can see this diagram. The different regions are given in the diagram, but already I explained you that is the elastic region. This one is the perfectly plastic or yielding region. From D to E, that is strain hardening region. From E to F, that is necking. Already I explained you each and every point of the diagram. This is a very, very important diagram, stress strain diagram for a ductile material. You have to refer this diagram. Each and every point is given A, B, C, D, E, and F. By using this diagram, few important points, that is nominal stress. Nominal stress is nothing but the stress which are calculated by dividing respective loads by original cross-sectional area are called as nominal stresses. From the stress strain curve, it is clear that nominal breaking stress is less than ultimate stress. So nominal breaking stress is equal to load at breaking point upon original cross-sectional area. See, again I am telling you, please highlight each and every formula because every formula is required to solve the problem. Please make a list of all the formulas so you will solve the problem very perfectly. Actual stress, this one is the nominal stress, this one is the actual stress. Actual stress are the stress which are calculated by dividing respective loads by the reduced cross-sectional area at the point are called as actual stresses. The actual breaking stress is the ratio of load at breaking point and the reduced cross-sectional area of the specimen at fracture. In stress strain curve, it is clear that the actual breaking stress is considerably higher than the ultimate stress as shown by dotted curve EF. Thus, actual breaking stress is equal to load at breaking point upon reduced cross-sectional area at a fracture. Please highlight each and every point. Another syllabus topic, that is yield stress. Yield stress, it is defined as the ratio of load at yield point and the original cross-section area of the specimen. So yield stress is equal to yield load upon original cross-sectional area. It is the nominal stress corresponding to the yield load. Another subtopic, that is ultimate stress. The ultimate stress is nothing but the ratio of maximum load that specimen is capable of withstanding and its original cross-sectional area is called as ultimate stress of the material. So ultimate stress is equal to maximum load upon original cross-sectional area. Ultimate stress is equal to maximum load upon original cross-sectional area. Please highlight each and every formula. It is the nominal stress corresponding to the maximum load. That is your ultimate stress. Next point, that is working stress, or you can say the allowable stress. See, all the points are very important in the third and final year also, because there will be a subject machine design. In the machine design, you have to use working stresses, allowable stresses, ultimate stress. So please note down all the formulas very clearly. This is not only for this chapter. This is for your entire design subjects. It is defined as the ratio of actual axial load and the original cross-section area of the specimen. Formula for working stress is nothing but actual axial load upon original cross-sectional area. So here working stress is the maximum allowable stress to which a material is subjected during its service period. For a safety of a structure, it is very essential that working stress should be within the elastic limit of a material. These stresses are generally determined by dividing the yield stress or ultimate stress by a number called factor of safety. So here working stress is equal to actual axial load upon original cross-section area. One more important topic, that is factor of safety. So that is also very important topic, that is factor of safety. Just here I am explaining you the formulas, definitions. After that, we will move towards the problem. I know sometimes the theory part is a boring part, but until and unless complete the theory parts, we cannot go to solve the problem. See, the syllabus topic, factor of safety. The ratio of ultimate stress to the working stress for a brittle material is called as factor of safety. The factor of safety is nothing but ultimate stress upon working stress. Already I explained you what is by ultimate stress and working stress. The ratio of yield stress to the working stress for a ductile material is called as factor of safety. See here you can say yield stress upon working stress. See, stress strain curve for brittle material is also different. In designing to resist accidental load, sufficient reserve strength is required to ensure, which is carried out by taking suitable factor is called as factor of safety. Factor of safety always greater than unity. Measurement of ductility. This is also important point. In a tension test, both percentage reduction in area up to fracture and the percentage elongation in gauge length of the specimen up to fracture are considered to be measure of ductility of a material. So here percentage reduction in area is nothing but original area minus final area upon original area into 100. So percentage elongation is equal to final length minus initial length upon initial length into 100. You can see this diagram. In this diagram, strain is given at x-axis, stress is given at y-axis. You can see from this point to this, that is stress strain diagram for brittle material. See, you can consider cast iron is a brittle material. For the brittle material, you will get this type of curve. In the previous case, means in the case of a ductile material, I explained you point A, B, C, D, E, and F. See, this is a stress strain diagram for brittle material. The graph shows stress against strain for a brittle material when subjected to tension. As already seen, mild steel is only material that shows well-defined yield point. Brittle materials like concrete, aluminium, cast iron has very low proportional limit and do not show the yielding point. In such a cases where the yielding point is not clearly defined, it is taken as the point of some definite amount of permanent strain, generally 0.2%. It is denoted by the offset method as shown in this figure. You can see proof stress is shown in the figure. It is 0.2%. It is obtained by offset method as shown in figure. So you can see this. This dotted line is shown and this one is also dotted line. The stress corresponding to the point B is called yield stress or proof stress. You can see here proof stress. For brittle materials, the stress strain graph is continuous curve from beginning itself. From beginning itself, that is continuous curve. The ultimate stress is not well defined, but the breaking stress at the point A is always defined, or you can say the A is well defined. Brittle materials has relatively small tensile strain up to point of rupture. See, this is a diagram for stress strain diagram for a brittle material. So the next syllabus point, that is linear strain. strain in the direction of applied force is known as linear strain, or you can say the primary strain. It is the ratio of change in length to the original length of a member. So the linear strain is equal to change in linear dimension upon original linear dimension. So E is equal to delta L upon L. Please highlight this formula. Now you have to highlight each and every formula, because while solving problem, all the formulas are required. So E is your strain, small e is your strain, delta L is your change in length of the body, and L is the original length of the body. See, capital E was the Young's modulus. This is your small e, that is strain. Lateral strain. Strain in the direction at right angles to the direction of applied force is known as lateral strain, or you can say the secondary strain. It is the ratio of change on lateral dimension to the original lateral dimension of member. So here lateral strain, that is change in lateral dimension upon original lateral dimension. For a rectangular bar, lateral strain, that is EL, is equal to delta B upon B, or delta T upon T. Delta B is change in width, delta T is change in thickness, B is the original width, and T is the original thickness. For a circular bar, lateral strain is nothing but a delta D by D. D is the original diameter, and a diameter of delta D is change in diameter. See, you can see this diagram. Steel rod is shown in figure. This one is your steel rod. Diameter is given, that is 20. P is applied load. You can see this is your applied load. The length is given, that is 200. After applying the load away from the body, that is tensile, that is the change in length, that is delta L. Whenever the length will increase, automatically there will be decrease in dimension, decrease in diameter. So in this case, linear strain is equal to delta L upon L. So this is your linear strain. And lateral strain, that is perpendicular to the applied load, the dimension is D. So delta D by D is a lateral strain. Here you will get negative sign because there is decrease in diameter, or you can say that it is compressive, so sign will be negative. Very important subtopic is there, that is Poisson's ratio. When homogeneous material is located within its elastic limit, the ratio of lateral strain to the linear strain is constant and is known as Poisson's ratio. It is denoted by mu, or 1 upon m. See, the ratio of lateral strain to the linear strain is constant, and that is known as Poisson's ratio. You can see the ratio of lateral strain to the linear strain, and it is denoted by mu, or you can say the 1 by m. So EL upon E, lateral strain is equal to minus mu into E. This one is the lateral strain, that is EL is equal to minus mu into E, or 1 upon m into E. See, few important points related to the Poisson's ratio. The value of m lies between 3 and 4 for most of metals. Means Poisson's ratio for most of the metals lies between 0.25 to 0.34. According to the Poisson's ratio, lateral strain decreases as longitudinal strain increases. That is, lateral strain is always opposite to linear strain. Therefore, the ratio is attached with a negative sign, but the Poisson ratio is always expressed as a positive value. So again, here I am explaining very important point. According to the Poisson's ratio, lateral strain decreases as a longitudinal strain increases. That is, lateral strain is always opposite to the linear strain. Therefore, this ratio is attached with negative sign, but Poisson's ratio is always expressed as a positive value. See, in the next video, we will see volumetric strain, uniaxial and biaxial and triaxial stresses. Thank you. Thank you very much.